Hello all, we're going to do an example today of differentiating an equation where there's a lot of different letters in them, and some of the letters are related to x, some of them are a function of x, and some of them are not. And so you'd like to be able to differentiate these types of things. This sort of skill is useful in physics and other areas outside of math. So we're going to go ahead and take a look at this. So the equation I've chosen, a little bit complicated to give us kind of a sample of everything, is going to be p times q squared plus r squared s is equal to p times s plus x cubed. And we're going to differentiate this with respect to x. So our variable of differentiation is x, meaning that if a letter is going to be a constant with respect to x, we are going to treat it as a constant in the function. In this case, p and q are going to be considered constants as x changes. And in this case, r and s are going to be functions. We are assuming that r changes and x changes as you change x. So this is what we're working with, and when we take the derivative with respect to x, we're going to treat all of these letters differently based on whether or not they are constants or they are functions. So just kind of for example on the side here, if g is a function of x, I'm going to treat it like a function, and so when I have to find the derivative of g squared with respect to x, I need to treat this as a function, and so there's a chain rule happening here. The inside function is g, the outside function is this something squared. So the derivative of this is the derivative of the outside, leave the inside alone, times the derivative of the inside. And there we go. So we need a chain rule in order to find this derivative because we are considering g to be a function of x. However, if g is a constant with respect to x, meaning that g is not changing as x changes, then we just regard this g squared as just a constant term. And as we know, when we take the derivative of a constant term, that derivative is going to be 0. So there we go. It's the same letter, but depending on how it's related to x, we treat it in very different ways. The same thing is going to happen here with p, q, r, and s. So let's go ahead and start our derivative. So we know that we have this p q squared plus r squared s is equal to ps plus x to the third power. Now p and q here, let me go ahead and erase this q and write it a little bit nicer. P and q are both going to be constants with respect to x. And so as x changes, neither p nor q changes, which means this entire pq squared term is a constant term. It does not change. And as we know, with derivatives, if you differentiate both of these sides with respect to x, the constant terms are going to disappear. So when we take the derivative of the left-hand side, the pq squared turns into 0. And now we have the r squared s. Now the r is a function of x, and the s is a function of x. And so r squared is one function of x, s is another. Because we are needing to take a derivative of a product of a function, a product of two functions of x, we are going to need a product rule here. So, fair enough, we'll just take the first function, r squared, times the derivative of the second function, and this is just ds dx, the derivative of s with respect to x. So first function times the derivative of the second, plus the second function, and the second function is s, times the derivative of the first, and the derivative of r squared, just like we found the derivative of g squared over here, the derivative of r squared is 2 times r times dr dx. And there, all of that is a product rule that finds us the derivative of the r squared s term. Alright, so we write the equal sign, p times s. P is constant, s is a function. And we remember that in the derivative, constants, when they're constant coefficients, are just left alone when you take the derivative. It's like there's a 3 sitting in front of this s, right? And so the derivative of p times s is just p times ds dx. And then plus, and x is the variable of differentiation, and so the derivative of x cubed is just the usual 3x squared. There's nothing really crazy there. And that's it. There's nothing else we have to do here. You could certainly take this 2 and move it in front of the s and the r, and you could get rid of these braces if you wanted to. But really our answer here is just going to be r squared ds dx plus 2rs dr ds, or dr dx, excuse me, is equal to p times ds dx plus 3x squared. And this is a relationship that holds, provided the first relationship, the original equation we gave, also holds. And that's it. That's how you take a derivative of an equation when you know some of the letters in the equation are constant with respect to the variable, and some of the letters in the equation are functions. So this is a little bit more advanced than some of the stuff we've done, but hopefully it helps. If you have any questions, go ahead and stop by my office or ask me in class. I'm happy to help. Anyway, happy mathing.